For the longest time, the image most of us have of how these giant AI language models work, well, it's that they're basically superpowered next word predictors, right?
Yeah.
Stringing sentences together one token at a time.
Mm-hmm. That's the standard picture.
But what if that wasn't the only path? What if
Yeah.
there was like another way to build really intelligent language tools, maybe even unlock stuff we haven't seen yet?
Well, it's interesting you say that because, yeah, the field has been overwhelmingly dominated by that autoregressive approach for years.
Right.
This next token prediction idea, it's driven incredible progress, no doubt. It powers so much the language tech we use every day.
Exactly. And that's why this deep dive is so fascinating. We're digging into a research paper from Ni and colleagues 2025 introducing large language diffusion models.
Yep.
And specifically, we're going to unpack their model, LLaDA.
So for you, the listener, maybe you're trying to keep up with all these AI breakthroughs. It's moving fast.
Yeah, incredibly fast.
This deep dive, our aim is to give you a really clear understanding of this new approach. We'll pull out the key stuff, show you why this research could be, well, a pretty big shift in how we think about language AI.
Yeah, this paper, Large Language Diffusion Models, it really kind of challenges that core assumption that autoregressive models are the only way to get smart language AI.
Right. Throws down the gauntlet a bit.
Totally. So our mission today is pretty straightforward. Let's get our heads around the core ideas of LLaDA, how it's different from the usual models and what potential this new direction might hold.
Sounds good. Let's do it.
Okay, so let's start with the established picture. For what feels like forever in AI time, these autoregressive models, ARMs think things like GPT, they've been king of the hill for large language models.
That's absolutely right. And the paper itself points out just how deep-rooted this next token prediction paradigm has become. These models learn by, well, predicting the next word in a sentence based on all the words that came before it. It's kind of like a super sophisticated version of your phone trying to guess the next word you're typing.
Precisely. And the paper mentions the big successes, right?
Yeah.
Bradford, Brown,
Yeah.
OpenAI. They built amazing models using exactly this method.
They did groundbreaking stuff.
Yeah.
And that very success is what makes the paper's central questions so important, so provocative, really.
Which is?
Is this next token prediction, this autoregressive way, truly the only way to get really advanced language understanding and generation, where we may be missing something else fundamental?
And the LLaDA researchers basically come in and say, hold on, maybe not.
Yeah.
Their big argument is that the key isn't just the autoregressive setup, it's the underlying principles of generative modeling itself.
Right, learning the deep patterns, the probabilities within language.
Exactly. And the autoregressive way is just one method to get at that.
What's really interesting here is that they're suggesting learning the overall sort of statistical fabric of language is what matters most. Autoregressive models focus on that sequential prediction, one after the other.
Left to right.
Yeah, left to right. But diffusion models, they take a completely different path to try to capture those same complex statistical relationships.
Which brings us right to LLaDA. That stands for Large Language Diffusion Model with Masking. And it's not just like a small change. They built this thing from scratch using a diffusion process.
Yeah, totally different foundation. And at its core, this diffusion idea, in the language context, it has these two main phases. First, there's this forward process. Think of it like taking a clear sentence and gradually randomly hiding words, masking token.
So like blurring it out.
Kind of, yeah, until it's mostly obscured. And then comes the really clever part, the reverse process.
Okay.
This is where LLaDA learns. It takes that heavily masked, jumbled up sequence, and it learns to iteratively predict the original words, filling in the blanks step by step. Ah, okay, so it's like reconstructing that blurry image, but with words instead of pixels.
Exactly.
Well, one of the biggest differences, and maybe the most important, is how the model actually sees the information. ARMs read and write sequentially, right, left to right.
Yeah?
LLaDA, because it masks things all over the place and then reconstructs, it can actually consider the entire input sequence simultaneously when making a prediction for any given spot.
Ah.
The paper calls this having bidirectional dependencies.
Bidirectional. So it can look forwards and backwards in the sentence at the same time.
Exactly. Unlike ARMs, which are inherently stuck looking only backwards, this hints at potentially a more holistic grasp of meaning and relationships within the text. It's not tied to that one-way flow of information.
That makes a lot of sense. So when it's trying to predict a masked word, it sees the context before and after it.
Right.
And the paper says this is really good for reversal reasoning tasks. What exactly are those? I think you mentioned them earlier.
Yeah, so these are situations where knowing a relationship one way should logically mean you know it the other way too. Simple example. If a model learns A is B, you'd hope it also understands the implication that B is related to A, or can infer things based on that reversed understanding.
Like the cat sat on the mat versus the mat was sat on by the cat.
Something like that, yeah. Or even more abstract relationships. Autoregressive models, because of their left-to-right nature, often stumble on this kind of reversal. They learn the forward direction well, but the reverse, not so much.
Okay, this is where it gets really interesting then. The paper shows some pretty strong evidence for what LLaDA can do. A key thing is scalability, right?
Yes, absolutely. They show that as they pump more resources, more data, more compute into LLaDA, its performance on benchmarks, things like MMLU for general knowledge, GSM-8K for math problems, it scales up nicely.
And importantly,
it reaches performance levels comparable to autoregressive models that they built themselves as baselines for comparison. Figure 1 in the paper really highlights this, showing competitive results in zero-shot and few-shot learning.
so the scaling magic we've seen with A-arms isn't exclusive to A-arms. Diffusion can scale too.
That seems to be the message, which, if you think about it, suggests that these fundamental generative modeling principles, whether through diffusion or autoregression, can lead to powerful, scalable AI if you engineer them right. It opens up new avenues.
And it's not just about test scores. LLaDA also shows strong in-context learning.
That's right. Their 8 billion parameter LLaDA model performs competitively against really strong models like LAMA3-8B.
Wow.
Specifically in its ability to learn on the fly from examples given right there in the prompt.
So for you, the listener, this is important. It means LLaDA isn't just spitting back stuff from its training. It can actually adapt to new tasks you show it, just based on a few examples. That makes potentially much more flexible.
Definitely. And that ability, which they detail in Table 1, is super important for modern LLMs. It's what lets them handle new situations without needing a whole new training cycle for every little thing. The fact that LLaDA, with its completely different architecture, nails this is, well, it's noteworthy.
And then they did more training, right? Supervised fine-tuning, SFT.
Yes, they fine-tuned it specifically on instruction-following data, lots of examples of prompts and desired answers.
And the result?
Even better at understanding and carrying out complex instructions. They show examples in Table 4, things like holding a multi-turn conversation coherently. It gets pretty impressive.
So the diffusion approach isn't just about generating text. It can be steered, aligned with what humans want it to do.
Exactly, which is obviously critical if you want to actually use these things in the real world.
Okay, but maybe the most surprising thing, the bit that really makes you go, huh, is how LLaDA deals with this reversal curse.
Ah, yes, the reversal curse.
I explained it a bit. Models trained on X is Y often mess up. Y is X.
Right. It's a known weakness, particularly for autoregressive models. And LLaDA seems to handle this remarkably well. Table 3 in the paper shows it even outperforming GPT-4o on a specific task involving completing reversed poems.
Wait, hang on. Outperforming GPT-4o, the big recent OpenAI model.
On that specific reversal task, yes. That's a pretty huge statement about the potential here.
Wow. Okay. Yeah. Tell me more about that poem example.
Yeah, they have this great example in Appendix B.8. It's a classic Chinese poem, A.G. Fi, where the lines have a clear forward and reversed relationship in meaning. LLaDA apparently did a much better job capturing that reverse meaning compared to the other models they tested.
And that really comes back to the bidirectional thing, doesn't it?
Almost certainly. LLaDA doesn't have that built-in left-to-right bias. It can see the whole picture, potentially letting it grasp these symmetrical relationships more naturally than a model that's forced to process things in one direction. It suggests a deeper, more flexible understanding.
Okay, so it can do some cool stuff. How do they actually train it? You mentioned it takes a lot of resources.
It does. The paper outlines the process. It's kind of a standard pipeline in principle. First, pre-training on just a massive amount of text, then supervised fine-tuning, or SFT, and finally, lots of evaluation.
And that pre-training data set was huge.
Immense. 2.3 trillion tokens. And yeah, the compute cost they mentioned is substantial, 0.13 million hours on H800 GPUs. That's serious hardware time.
So does that mean diffusion models are just inherently way more expensive to train right now?
It certainly highlights the significant resources needed, yeah. It's hard to make a direct cost comparison just from this paper as they optimize different things, but training LLaDA was clearly a major undertaking.
And during that pre-training, they used that random masking you talked about.
Correct. And crucially, the amount of masking varied randomly for each sequence, anywhere from 0% to 100%. They contrast this with models like BERT, which usually use a fixed percentage of masking.
Why the random amount?
The thinking is that this dynamic masking forces the model to learn language structure at multiple levels of granularity, making it more robust for generation. Then, for the fine-tuning, the SFT stage, they used about 4.5 million pairs of prompts and good responses.
Okay.
And interestingly, even during SFT, they applied masking, but this time specifically to the response part of the examples.
So it's always learning to fill in the blanks, essentially.
In a sense, yes. Always practicing that reconstruction.
And then when you actually want LLaDA to generate text, say, write a paragraph or answer a question, the inference part, how does that work with all the masking?
Good question. It actually starts with a sequence of entirely masked tokens representing the length of the output you want.
Okay, so a blank slate of masks.
Pretty much. And then LLaDA iteratively predicts the tokens to replace those masks, refining its prediction over several steps. The paper mentions there's a trade-off. More prediction steps generally gives you better quality text.
But takes longer and costs more compute.
Exactly. So you balance the number of sampling steps based on whether you need top quality or faster output.
Got it. So the paper piles up quite a bit of evidence for LLaDA's abilities.
Yeah.
Can we just quickly recap the highlights they emphasize?
Sure. So as we touched on, Figure 3 really drives home the scalability point across different tasks.
Right.
Table 1 gives those direct benchmark comparisons, showing LLaDA 8B holding its own against established models like LLaMA 2.7b and even LLaMA 3.8b in zero-shot and few-shot settings.
And it had particular strengths.
Yeah, they noted particularly good performance in math and also in Chinese language tasks.
Okay. And the instruction following after SFT.
Big improvements there shown in Table 2. They mention it might be slightly behind models that use reinforcement learning from human feedback, RLHF, for alignment.
Which is another training technique.
Right. But LLaDA's performance with just SFT is still really quite strong, showing the core model can be aligned effectively.
And we definitely can't forget the reversal reasoning success.
Absolutely not. That's Table 3, a key result. And finally, those case studies in Table 4 provide the qualitative proof, showing it generating coherent text, engaging in sensible multi-turn dialogues. It looks and feels like a capable language model.
Now, with any big new research like this, it's always good to look at potential caveats or nuances. Did the paper address any concerns?
They did, yeah. They acknowledge one point about computational cost versus likelihood. They mentioned that technically their diffusion model might need more compute than an ARM to achieve the exact same score on a metric called likelihood.
Which is like how probable the training data is according to the model.
Kinda, yeah. But they rightly point out that likelihood isn't the be-all and end-all for how well a model performs on actual downstream tasks, like reasoning or translation. Diffusion models optimize a different mathematical objective anyway, so it's not quite an apples-to-apples comparison just looking at likelihood.
That's a fair point. Performance on real tasks matters more. What about data leakage? The worry that the model just memorized answers from its training data.
Yeah, that's always a concern with huge data sets. They did try to address this. For example, with the GSM-8K math problems, they tested LLaDA on a specially created unseen data set called IGSM, which they detail in an appendix.
And how did it do?
It still performed well on this completely new data, which suggests it wasn't just recalling answers it had seen before, but actually learning the underlying mathematical reasoning skills.
That's good diligence.
Okay.
So wrapping this up then, for you, the learner, listening in, what's the single most important takeaway from this deep dive into LLaDA?
I think it's this. Diffusion models, and LLaDA is a prime example here, are seriously emerging as a viable, competitive alternative to the autoregressive approach that has dominated LLMs for so long.
Yeah, it's not the only game in town anymore.
Exactly. And the real aha moment, I think, is realizing that all these amazing abilities we see in LLMs, learning on the fly from prompts, following instructions, even complex reasoning, they might not be inherently tied to just predicting the next word. LLaDA's success, especially beating the reversal curse without that left-to-right constraint, really hammers that home. There might be other ways to build intelligence.
And the implications of that could be pretty huge, couldn't they?
Potentially, yes. This could open the door to totally new AI architectures, maybe models that are more robust in some ways or more efficient for certain tasks, or maybe they excel at things current models just aren't good at yet.
It definitely widens the design space for AI.
It really does. And it leaves you, the listener, with a fascinating question to chew on. If the core principles of generative modeling are the real key, not just the specific autoregressive recipe we've been using, well, what other surprising architectures might pop up? What other ways are there to model language probability? What kinds of capabilities, maybe ones we haven't even imagined, could those new approaches unlock? It really pushes us to think beyond the established ways of doing things.
A really provocative thought to end on. This deep dive, hopefully, has given you a solid grasp of LLaDA and why large language diffusion models are generating so much excitement.
Yeah, definitely a space to watch.
Yeah, absolutely. We definitely encourage you to stay curious and keep an eye out for what comes next in this really fast-moving field.